Okay, let's look at this important lemma. And this lemma is important because we're really going to need it to prove the really important theorem that I call the buy two, get one free theorem. Before we actually prove the lemma, let's read it and see how it actually pretty much proves the theorem. So what this says is, suppose you have a subspace of RC with dimension U equals n. So that means there's a basis of U with n vectors in it that is linearly independent. And also suppose that V is another list of n vectors, so the same number of vectors as a basis. What this says is that V is linearly dependent if and only if V does not span U. Now remember, if and only if means if one of these two things is true, then the other one is true. And if one of them is false, the other one is also false. So another way to write this is like so. V is independent if and only if the span of V equals U. And that's the way we're really going to use the theorem, but it's going to be easier to prove in this like opposite version. So we'll prove this in a minute, but before that, let's see how that applies to the buy two, get one free theorem. So this says if you have a list of vectors that are vectors that are all in some subspace U of RC, if any two of the following are true, then so is the third. Now, let's just justify why this is. If 2 and 3 are true, that implies that 1 is true because that's the definition of the dimension. Like, if these two things are true, then that means that your list of n vectors is a basis, and the definition of dimension is the number of things in a basis. Okay, now what if number 1 and 2 are true? If you have the same number of vectors as a basis and it's linearly independent, then we can use this lemma. You have the same number of vectors as a basis, and if the list is independent, that means it spans U. And likewise, if 1 and 3 are true, if you have the same number of vectors as a basis and it spans U, then it must also be linearly independent, according to the above lemma. So this theorem is really a kind of more convenient way of repackaging what the lemma says. But the lemma is in an easier format to prove. So let's prove it. So first of all, there's a weird edge case where if you have n equals 0, like a list of no vectors, that means your list of vectors is just the empty list, then it's an exercise to prove it. So we'll leave that as homework, I guess. So let's assume that we have at least one vector. And we have two things we're going to prove. We're going to prove if V is linearly dependent, then it doesn't span U. Now, that means one of the vectors can be written as a linear combination of the others. That's the characterization of linear dependence theorem from section 1.4. And that vector can be removed without changing the span. Which was theorem 1.15 or something in the last section. And And we can repeat this process until you have a linearly independent sublist W smaller than V. This process has to stop at some point because, like, if the smaller sublist continues to be linearly dependent after removing all the vectors, and you're left with W as just the empty list, then that's defined to be linearly independent too. Okay. Since all bases of U have n vectors, the dimension of U, that's because all bases of any subspace have the same number of vectors, and there's one with n, which is what that means. And W has fewer than n vectors because V has n vectors and W has some vectors removed from it because V was linearly dependent. We can conclude that W is not a basis of U. And we know it's linearly independent, so the reason it must not be a basis is because it doesn't span U. But we know the span of V and the span of W are the same because we removed the linearly dependent vectors without changing the span. And so the span of V must also be not equal to U. So that shows that if V is linearly dependent, then it doesn't span U. Now we need to show the other direction. So if we suppose the span of V is not U, and we want to show it's linearly dependent, there must be some vector in the subspace U that's not in the span of V, because all the vectors in the span of V must be in U, right? Because we said the Vn, V1 through Vn vectors are all in U, and U is closed under scalar multiplication and vector addition. So we know there's some vector U in U, but not in the span of V. Now, if we take that one vector U that's not in the span of V, that list now has more vectors in it than a basis, because a basis must have n, because that's the dimension of U. And we just had a theorem earlier in the section that said if you have more vectors than a basis, you have a linearly dependent list. And that means, again, using theorem 1.6, the characterization of linear dependence, that one of these vectors must be a linear combination of the others. And it can't be the vector U, because U is not in the span of V. So that means one of the other vectors is a linear combination of the previous vectors. And that means the list V is linearly dependent. Okay, so that proves that lemma, and if you repackage the lemma into the buy two, get one free theorem, you get this nice handy theorem, which is going to be pretty useful. It basically says that if you have the right number of vectors in a list and it's either linearly independent or it spans U, then that means it's a basis. You don't need to prove the other one. Okay, so yeah, if that proof was tough, that's okay. Understanding this proof, I would say, is like bonus. If you get it, that's great. It is good to know what all of these theorems we're using are saying and see how that all works together to prove more complicated things. But I'm not going to give you a question this difficult on like one of my tests anyways. This would be like the level of an extra credit problem or something. Most of the proofs you have to do for homework are much simpler than that. So anyways, let's look at this definition. The dimension of the column space of A is called the rank of A, and you just write it as like rank A, like so. Now, the reason we don't just call it the dimension of the column space is because it's actually also equal to the dimension of the row space. And the reason for that is that we had a theorem in 1.6 that the pivot columns of A are a basis of the column space of A. So the number of pivot columns is the dimension of the column space. And we also had a theorem that the pivot rows of the reduced echelon matrix gives you a basis for the row space. So the number of pivot columns is equal to the number of pivot rows. So the dimension of the row space and dimension of the column space are both equal to the rank of A. They're both equal to the number of pivot positions you have in A. Okay, let's look at example 4. Here we have a 2 by 5 matrix. Let's row reduce this to see how many pivot columns we have, and also see what is the dimension of the null space. So first of all, I'm going to do one row operation. Let's clear away this -2 by doing 2 times the first row plus the second row to replace the second row. I'll leave the first row alone. And so yeah, at this point, it's in echelon form. We can see the rank is going to be 2 because we have 2 pivot columns in A. Because again, if you want a basis for the column space, it's the pivot columns of A. Okay, now let's get the dimension of the null space. So to get a basis for the null space, we're going to be using the standard method from section 1.4, where we get this all the way to reduced echelon form. To do that, let's scale row 2 by -1/3, like so. And then we can use row 2 to clear away this -5 here. So we're doing 5 row 2 plus row 1 to replace row 1. 5 times -2/3 is -10/3. Combines with 1 to make -7/3, right? And then 5 times 2 plus 2 is 12. So we have that. And from there, we can rewrite the system as x1 plus 3x2 minus 7/3 times x4. You know what? I just forgot that I didn't actually write the zeros over here. But you know that if there were zeros over here, doing all these row operations wouldn't change them. So we can just say they were there. It doesn't matter. And yeah, we can see that x1 and x3 are the basic variables, the pivot column variables, and x2 and x4 and x5 go along with the non-pivot columns there. And so we can write all the variables in terms of the free variables. x1 is equal to -3x2 plus 7/3 x4 minus 12x5. x2 is equal to x2 because it's free. x3 is a basic variable. And x4 and x5 are free. And of course, this is the same thing as saying, like, if we have this all written as a vector with equal components like this, you can write that as x2 times negative 3, 1, 0, 0, 0 plus x4 times 7 thirds, 0, 2 thirds, 1, 0 plus x5 times negative 12, 0, negative 2, 0, 1, like so. And these vectors form a basis for the null space. We know they span the null space because these equations being true here, that system of equations is equivalent to the original homogeneous system. And we also know that they're linearly independent because of the way that each one of them has a free variable as its coefficient. So whenever you do this method, you're going to get a 1 in a location where the other ones have zeros, like so. And that means none of them is a linear combination of the others. So yeah, this method is always going to give you a basis. And so the dimension of the null space is 3. And we have 3 because there are 3 non-pivot columns. So this is basically an argument for the rank-nullity theorem. It's called the rank-nullity theorem because the dimension of the null space is sometimes called the nullity. And so yeah, both of these add up to the total number of columns. And the reason for this, we've already explained why the rank of A is equal to the number of pivot columns, and the dimension of the null space is equal to the number of non-pivot columns. Because, as we've been saying, each one of the non-pivot columns gives you a free variable in the solution, and each one of those free variables corresponds with a vector in the basis that is going to be linearly independent from the other ones, the way you set it all up. And so that is the number of non-pivot columns, aka free variables. And those add up to the total number of columns. So that is basically a proof of that. So yeah, that's going to be a useful theorem sometimes. Coming up. Good luck with that. And I hope you're having a good day. And I hope linear algebra is going well. We've covered a whole lot of the main ideas. In the next chapter, we're going to start looking at matrices as their own thing. See how to multiply matrices together. What are the properties of matrix multiplication? And then from there, we're going to do all kinds of stuff with that in chapters 3, 4, 5, 6, and 7. See you later.